Today, we will be talking about electric forces and electric fields. Electric charges follow a certain set of properties. Charge is conserved, meaning charge can never be created or destroyed. Like charges will repel each other, and opposite charges will attract each other. Electric force is the force exerted by a charge onto another charge. This force is defined by Coulomb's law. Ke is Coulomb's constant, about 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Q1 and Q2 are the individual charges, and R is the distance between them. The force is measured, of course, in newtons. Electric field is given off by charges. It is measured at a point in space in units of newtons per coulomb. What it means is if a charge were placed in the vicinity of an electric field, a force would be exerted on that charge. Electric fields are not unlike gravitational fields. Charges will pull in opposite charges and push away like charges, depending on how close the two charges are to each other. In our first example, we have two charges separated by 2 meters. One of the charges is negative and one is positive, so we expect them to attract each other. We can use Coulomb's law here. The first charge is negative 2 microcoulombs, and the second is positive 1 microcoulombs. The distance between them is 2 meters. Substituting in our value for Ke and multiplying through, we have 4.5 times 10 to the minus third newtons. This is an attractive force, meaning the charges will pull on each other. In our second example, we have a square arrangement. We would like to find the net force acting on Q3, the negative 2 microcoulomb charge. We can find the net force by adding up the individual forces exerted by Q1, Q2, and Q4 on Q3. Q1, because it is positive, will exert an attractive force on the negatively charged Q3. Using Coulomb's law, we have 3 microcoulombs and negative 2 microcoulombs for the value of the charges. Because the distance can be measured as the hypotenuse of a triangle, we can use the Pythagorean theorem to find the hypotenuse as the square root of the sum of the squares of the side lengths, being 25 centimeters, or 0.25 meters. Multiplying through, we have a total force of Q1 on Q3 of 0.432 newtons. The force of Q2 on Q3 will be repulsive because they are both negative charges. Plugging in our numbers to Coulomb's law, we have a force of 0.345 newtons. The force of charge 4 on charge 3 is also repulsive as they are both negative. Plugging in our numbers, we reach a force also of 0.345 newtons. Each of the forces exerted by 2 and 4 are repulsive, so they will push in the east and south directions. The force exerted by charge 1 on charge 3, however, is attractive. We can find the x and y components of charge 1 on charge 3 by multiplying the magnitude of the force by cosine of 45 and sine of 45. Now we've found our total x and y components by adding each of the individual ones for each separate charge. With these values, we can square them, add them, and then take the square root to find our total force. Plugging in our numbers, we reach a total force of 0.057 newtons. To find the angle that this force is exerted at, we take the tangent inverse of the y component over the x component. Plugging in our numbers, we have negative 45 degrees. In our third example, we would like to find the electric field at the marked location on the line between two charges. Because the first charge is negative, it will exert an inward electric field. The second charge is positive, so the electric field would be exerted outward. We can use our formula for electric field to find the electric field at this point. If we find the electric field due to Q1, and then find the electric field due to Q2, we can add them together for the total electric field. For Q1, we have negative 8 microcoulombs and a distance of 0.3 meters. Thus, the electric field due to charge 1 is 8 times 10 to the 5th newtons per coulomb. For the second charge, we have a value of 4 microcoulombs and a distance of 0.2 meters. So, we have 9 times 10 to the 5th newtons per coulomb. Because each of these point in the same direction, to the left, towards the negative charge, we can add them together to get a total of 1.7 times 10 to the 6th newtons per coulomb. This is the electric field at the marked point.